Okay, good morning, everyone. I hope you all had a happy new year and sort of recovered some energy over the vacations to start into this new year. And yeah, I noticed I still haven't, or noticed today in the morning, I still haven't uploaded the old exercise sheet. Probably if I get to do it, I have a kind of busy afternoon. I'm gonna upload this as well as at least one new exercise sheets, right? I noticed that I had kind of the concerning the material that we've covered already at least one new old exercise sheet ready that you will be able to look into. And okay, good. Is there any other housekeeping points? Okay, we need I think the two things we need is a date for the re-exam still, right? So we do have a date for the main exam. I think I even I posted this on the website. 27th. Exactly. Good. The 27th of February. And good. So for the re-exam, I don't know, let me maybe pull up the calendar Semestertermine. Okay, so the new summer term starts already the 15th of April. That means if we do a re-exam, we should do it proper before that. I also do have the one second. Good. The calendar of exams. Let me see if there's already something in the beginning of April. Oh, yes, of course. All the re-exams are already lumped. Oh my God. Okay, yeah, that's well, there's even an exam on Saturday. Interesting. Math for computer scientists. Interesting. They put this on the 29th. Okay, but I think it doesn't matter if we have a, let's say, collision with ethics for nerds or MFN1. What's MFN1? MFN? Anyone? I don't know. Let me click on it. No. See more details. No, it doesn't tell me what that is. Okay, good. Math for natural scientists, mobile security. Yeah, the calendar is already pretty dense. Cannot collide with security. Wow. So something like, oh, I see the 12th of March, which is too soon to the main exam. Probably there's going to be people. Yeah, so probably we're gonna drop it at something. Yeah, there will be collisions. So does anyone here still need to take an exam like linear algebra? Probably not. Good. Okay. Compiler construction, programming 2, introduction into computer linguistics. If not, then I think we're gonna probably go for Wednesday, the 2nd of April. Let me write an email. Draft. Second of the 4th. Good. Then let me see if we can do that. But okay, are there any questions still? Maybe concerning our. Let me again go to the calendar. The winter term. So when is the winter term over? The 9th of February. Okay. So we have to do the second quiz at some point before the 9th of February. Let me pull up my calendar. I would say, yeah, we do the 3rd of February. That's, oh yeah, okay, no, probably, yeah, let's focus. Yes. I believe there was a class on an exam on the 16th, right? The 16th of the midterm exam. And well, my question. What midterm exam of what? This class. A few questions that we have to do in the class. The quiz. It's not a midterm exam. It was a quiz. Midterm exam goes into your grade. A quiz does not. Yes. So about the your ask. Did you upload the lecture? The slides or the video of that one? I have to. I was sick and I had to leave and I didn't watch it. Ooh, let's see. I don't remember. Good question. So when it was the midterm, it could. Did I record last time? Yes. I did. Okay, then I don't know. Let me see. Maybe I did upload YouTube. Maybe I did upload. Wait, you were here for the quiz, but then not for the. Then you left for the interest. Ah, okay. I see. Okay, no, that's fine. So YouTube Studio. Okay, content. When was this? The 16th. Yes. I didn't drop the link of that. And let's see, this is lecture. Materials. 4.3. Oh, I did. I think this is correct. Yeah. This video is already uploaded. So, you know what? Before I forget it, let me quickly drop the. Of course, I didn't. Yeah, no, good. Then I didn't have I don't have the marked version of the quiz, but then let me also upload the quiz. But then let's maybe get into this lecture. We're already 10 minutes in. So where did we leave off last time? Which probably was the 16th, right? We looked at the Bonnet-Franklin crypto system, which in its form as an identity-based key encapsulation mechanism, right? Both encryption and decryption here, they're typically called encapsulation and decapsulation, produce a key, right? Encryption doesn't take a message as an input, but just outputs a key, and decapsulation or decryption also outputs the same key, right? You vaguely remember the scheme. It has similarities to Jou's key exchange, where we kind of pretend that the third party, right, in this key exchange is a sort of a virtual party whose message or public key is this h of id, right? Instead of some g to the z, or we have this h of id, and that's our third party. Okay, we looked at correctness, pretty simple, and then we look at the security proof, and or the security statement is given that the bilinear Diffie-Hellman assumption holds in this bilinear group, and the hash function h is modeled as a random oracle, then the Bonnet-Franklin scheme is int IB chem secure, right? I'm not going to go too deeply again into the security notion, but what was our proof strategy, right? Our reduction gets our reduction against BDH, gets as input a BD. What's happening now? A BDH challenge, which is something of this form: g to the x, g to the r, d to the z, and k star, where k star is either EGG to the XRZ or chosen uniformly random, right? By the way, this is K star, I see, or K star uniformly random. Good. The BDH adversary B has to distinguish these two distributions, right? And what does it do? Of course, it simulates the int IB chem experiment for the adversary A, where its superpower, so to speak, is to also be able to simulate the random oracle, right? So it runs this int IB chem experiment with A, but so it uses g to the x as the master public key. It puts it into a bit of an impasse because it doesn't know the corresponding master secret key, x, right? If it knew x, then solving its challenge would be trivial. So what does it do instead? It simulates the user secret keys or identity secret keys by simulating the random oracle H. So every time the adversary queries the random oracle on some identity, let's call it I, the adversary doesn't choose just a uniformly random group element, but he chooses a uniformly random group element together with its discrete logarithm in basis G, right? So what it does is it chooses a random ZQ element Ci and sets the output to be G to the Zi. And of course, if the index I is the challenge index that we've guessed before, then we output this G to the Z, which is part of our challenge, right? So for that key, we will not be able to, or for that identity, we will not be able to produce a identity secret key, but this is fine, right? Because we're hoping that I star will be the challenge, or it I star will be the challenge identity that he uses. Probability for that is 1 over q, which is polynomial, right? So that's fine. In that case, everything's good because the adversary is anyway not allowed to learn the user secret key or identity secret key for the challenge identity. Good. So that's how we simulate the random oracle. And how do we simulate keygen? If for given identity if the adversary has already queried the random oracle on this identity it, then great. Then we know the corresponding ZP element ZI. Otherwise, we're gonna query the random oracle for him, right? If he hasn't queried it before, well, let's query it for him. I mean, there's nothing the adversary can win, so to speak, by postponing these queries to the random oracle. And now we're simulating this HID to the X by computing MPK to the ZI. Right? By computing MPK to the ZI, this is just G to the X times ZI. MPK is G to the X. But now we're just flipping the order. Then we have G to the ZI, which is H of it to the X. So this H of it to the X, that's a well-formed user secret key. And for the challenge, good. And for the challenge ciphertext, right? Of course, we want that the adversary has queried the random oracle on it star. If he hasn't done it, we query it on his behalf. And if it star is not it I star, right? Then, well, too bad. Then we abort and output a random bit. Right, the probability that this happens, that it star is not it I star, we're going to look at this in a moment, is at most 1 minus 1 over q. So it's still bounded away from 1. And otherwise, we're in good shape. If it star is it I star, then we set the challenge ciphertext C star to be G to the R. And we set the key to be K star, right? Remember that in the int IB chem experiment, now I went too far. Where are we? Good. In the int IB chem experiment, the adversary gets both K star and C star, right? So his goal is to distinguish K star from being a well-formed key that came out of key encapsulation and just being a uniformly random key. Okay, but whoops, we're almost done here. That's the entire reduction. Now we just have to analyze it. So first of all, notice we note that A makes at most Q queries to H. And I star chosen uniformly random for the random. That means the probability that it star is the same as it I star, right, is at least 1 over Q, right? There's Q queries, and we or at most Q queries, right? Let's say, think of it, there were exactly Q queries, then this probability would be exactly 1 over Q. But since he makes at most Q queries, this probability can only be bigger if he makes less queries, right? Good. Okay, good. So that's the first thing, right? So this event that we're hoping for, that our it star equals it I star, this event here, this happens with noticeable probability, right? 1 over Q, inverse polynomial, at least inverse polynomial probability. So now we're gonna do the usual thing, right? And first assume that or look at what happens if the reductions input is this K star is actually EGG to the XRZ. So we have two cases. Now we have case one, K star equals EGG to the XRZ. Right? By the way, let's now for now condition on it star equals it I star. Right? Now we assume this good event actually happens. We're gonna deal with a case that it doesn't happen in a moment, right? If it doesn't happen, the reduction will anyway just output a random bit. Good, but now in the first case, if K star is the same as EGG to the XRZ, what happens now from the view of the adversary? Right, so the adversary sees all these things that the adversary A sees all these things that the reduction B simulated for him. What happens from his perspective? What does this experiment look like? Let's go here. So here, that's basically the case that K star equals K, the key generated by encapsulation, right? So what happens here, if we look at everything, in this case, B simulates the int IB chem experiment exactly for the case B equals 0, right? B or from the view of A, let's say that, let's be precise on this. From the view of A, B's simulation is simulated identically to the int IB chem experiment with B equals 0, right? So everything is like in the int IB chem experiment. We've said that the keys generated by our reduction B are identically distributed to those in the int IB chem experiment, and also the random oracle is simulated faithfully, right? The mere fact that the reduction B knows the discrete logarithms of these h of its that it outputs, that cannot be observed by the adversary A, right? The adversary has no way of telling whether he's sitting in this box here, in this simulation, in this matrix created by B, or if he's in the real world, right? For him, those two are indistinguishable. And in fact, if K star is EGG to the XRZ, then really the simulation of B is identically distributed to the actual int IB chem experiment with B equals 0, right? Because in this case, the key K is correct. And as a matter of fact, this is how we built our reduction key, right? This doesn't happen by coincidence. This is precisely the purpose of this reduction is to make this simulation that it runs to look like the real experiment from the view of A. Okay, this is the case that K star is EGG to the XRZ. But then again, let's go to case 2. K star uniformly random. So who can tell me what happens now? What does this look like from the view of an A? Think for a moment that A is all powerful. Right? Of course, our A is a PPT machine, but even if you were all powerful, what does it look like now? Even for an all powerful A. Yeah.
With respect to the situation of B again, or maybe it doesn't.
We just had the case challenge bit B equals 0. So what is this now? If we just had challenge bit B equal, yes? Exactly. So B's simulation identical to int I B chem experiment with B equals 1. Amazing. Good. So and now we're just, let's say, one use of the law of total probability away from getting the advantage of our reduction, right? So what's the advantage of B? Whoops. Good. Advantage of B is what? Well, it's I'm going to leave the absolute value away. Probability of B G to the X, G to the R, G to the Z, E, G to the X, R, Z equals 1 minus probability B of G to the X, G to the R, G to the Z, and something uniform equals 1. Right? So let's write this out. This here is almost case 1, right? The one thing that we still have to do is to condition that the thing we're hoping for actually happens. This it star equals it I star, right? So let's do that on for both of these. So I might have to write a little bit smaller. You know what? So that I don't have to write out these lengthy statements here. Let me just call this event here B0 and this event here B1. Right now, I can save myself some writing. So this is the probability of B0 conditioned on it star equals it I star times probability it star equals it I star plus probability B0 conditioned on it star equals it I star times not equal probability it star not equals it I star, and the same for the second event B1, probability B1 conditioned on it star equals it I star, probability it star equals it, still enough writing here, and probability B1 conditioned it star equals it I star, it's probability it star equals it I star. Okay. Now, unequal. Thank you. Thank you. Also, good. That's correct. Okay, good. So let's first do the simple things, and let's do them in a different color. No, I didn't. That was not a nice parenthesis. This guy and this guy. What do we know about those? What does the reduction, my reduction B do if it made a wrong guess? If it misguessed the challenge identity it star, or the index I star of the challenge identity it star, what happens then? Let's just scroll up and see what I wrote. Zip. Wait. Here. If it star equal, why did I write this? If it equals, okay, good. No. Here, if it star is different from it I star, then my reduction B just outputs a random bit. So what's the probability of guessing B correctly if my reduction outputs a random bit? What's the winning? Yes? Exactly. So in both cases, this is 1/2, and also here 1/2. Good. So now let's go for these probabilities here. What is this? So, and remember, B0 is B outputting 1 on input G, G to the X, G to the R, D to the Z, and EGG to the XRZ. Anyone? Yes?
It should be also 1/2.
Why? Then I think then we would lose, right? If you think a bit about it, if everything's 1/2, so sorry to cut you short, but this is exactly the case one we looked into. We said for now condition on it star equals it I star, right? Then if K star is EGG to the XRZ, and that's exactly what happens in this B0, then we're in case 1, right? And so we said in case 1, from the view of A from the view of a B simulation is identically distributed identically to int IB chem to the int IB chem experiment with B equals 0, right? This is now the probability, the same as probability int IB chem of A equals 1 conditioned on B equals 0. Okay, and then what's the last probability here? The B1. That's the case 2 we looked into, right? That's here in B1 we're getting a uniformly random key. So this is the same as what's happening in case 2. So this is the same as probability int IB chem of A equals 1 conditioned on B equals 1. And now we're almost good here. So let's write this out. So this is probability so what's the good? Let's quickly get over that. What's the yeah. No, let me just write it out. So we have probability int IB chem of A equals 1 conditioned on B equals 0. Oh, by the way, I blundered the minus signs here. I was just wondering, where did the minus sign go? Minus. So now that we have the correct minus signs, we can also see what happens here. What happens with those two probabilities here, with this one and that one? They're the same, right? So now that I did this correctly, they are just canceling out. And we're left with simpler expression int IB chem of A equals 1 condition B equals 1. And the whole thing, let's write it in front. Right, we have this probability it star equals it I star. Well, we knew this is greater than 1 over Q. Okay, so finally, what's this expression here? This is just a different way of writing the advantage of our adversary, right? We could maybe let me put this. This is just a little reformulation, but this is just the advantage in the int IB chem experiment. Whoops. Int IB chem of A. Okay. So, and did we call that epsilon? Good, with advantage epsilon. So this is greater equal epsilon. By the way, let's say let's put this on exercise. And again, this is really this step here to see that this is the advantage of A. That's again just using the law of total probability, right? So good. I mean, you just have to rewrite. It could be that it's 2 times. No, it shouldn't be 2 times the advantage. This should just be the advantage of A. Right, and good. And we said epsilon is non-negligible and Q is polynomial, so we get our desired contradiction against hardness of BDH. That concludes the proof, right? Because now we built an algorithm B, which distinguishes the BDH assumption with non-negligible advantage. So this is non-negligible. Okay, good. But again, these analyses are, now that we've seen this a few times, are always going the same way, right? The reduction gets us input a challenge, and sort of around this challenge simulates the experiment that the adversary expects, and kind of carefully embeds this challenge at a point where, or in a way that if the adversary can distinguish, it can help the reduction or it will enable the reduction to distinguish this its own challenge. Good. Okay, good. Is there anything left? I don't think so. Are there maybe any questions concerning this? Yes.
I think you explained this at the very beginning, but this epsilon, this non-negligible epsilon.
Yes.
Where this part you write that it is non-negligible?
Good. I mean, how it's been a while, right? It's been like 3 weeks, probably. Yeah, 3 weeks since we discussed this. We want to arrive at a contradiction, right? We want to say, okay, let's for a moment assume our key encapsulation mechanism, the Bonnet-Franklin key encapsulation mechanism, is not secure, right? What does that mean? Well, there is an adversary who defeats the int IBChem experiment. And what does it mean for an adversary defeating this experiment? Well, it means guessing the challenge bit B correctly with non-negligible advantage epsilon.
Definition.
Exactly. No, I mean, precisely. I mean, we typically just tuck this away, right? But again, almost any security proof is indirect or a proof by contraposition, in that we assume the scheme that we want to show secure is insecure, and then we deduce that if this was the case, then the hardness assumption we had made was wrong, right? And here we just deduced if the scheme was insecure, then the BDH assumption would not hold, because we just constructed an adversary who breaks who distinguishes the BDH assumption with non-negligible advantage epsilon divided by Q. This is maybe good sometimes to recall these things. Okay, good. So this much so far about identity-based encryption. This was sort of really the first, the first real killer app for bilinear maps. But then things around the same time, right? This was in 2001, kept moving, and let's look at another. Whoops. Another. What time is it? We still have, wait, that's not, no, we have 10:59. We have 45 minutes. So we have 45 minutes left, right? Or am I? Yeah, good. I just lost a bit track of time. Okay. So we've just seen the Bonnet-Franklin crypto system, identity-based encryption. And now we're sort of seeing the next, let's say, cool thing that came out of this, namely homomorphic encryption, or sort of a encryption scheme with non-true. No, not now. What is he doing? Oh, 1 second. That's a weird time for him to call me. Can I just pause for a moment and sorry, that's 1 second. When your kid calls you, that is very weird. Okay. Let me see if he tries to call me back. Then I would pick up this call. Good. Good. So now we are gonna talk about homomorphic encryption. Which is another example of how bilinear maps can be used to construct an encryption scheme with enhanced functionality, right? Sort of in terms of security, we said that in the very beginning, the kind of encryption schemes that we've seen in the very beginning, like Kramer-Shoup, give us everything we want, right? Int CCA2 security is, in a certain sense, best possible, right? But now we're after encryption schemes with more functionality that allow us to do more things. So in the case of IBE, we've seen encryption schemes that have a sort of delegation property. Someone who owns the master secret key can delegate identity secret keys, right? If I have the master secret key, I can decrypt any identity-based ciphertext. This is well, both a blessing and a curse if you think about it. If you want to use IBE in the way it was originally envisioned, right? You have this key is crow problem. If somehow the master secret key is leaked, then the security of every single user in the system is compromised, right? So people have come up with better use cases of IBE, and as a matter of fact, IBE itself is a really great tool to build other cryptographic protocols on top of it, right? But the originally pitched use case is, well, not the ideal use case for this concept. Good. So now, when it comes to homomorphic encryption, right? These are schemes where someone gives me a, let's see if I'm already starting with the correctness definition here. But in homomorphic encryption, what I want to do is someone gives me encryptions of messages, and now I want to be able to compute on these messages without decrypting them, right? Without decrypting these ciphertexts first. And where have we seen sort of something slightly to this effect, right? Encryption schemes that allow to kind of manipulate ciphertexts. Yes?
Was it the CTA attack?
That was exactly. That was precisely the attack against the, let's say, CCA security of El-Gamal, right? So El-Gamal is not cannot be CCA secure, or vanilla El-Gamal is provably not CCA secure, because ciphertexts can be manipulated, right? Give me a ciphertext, let's say, encrypting a zero. Yes.
Sorry, did you say vanilla El-Gamal or
vanilla El-Gamal? Yeah, there's. I did say you're familiar with this expression. Vanilla means without modifications. Textbook. Okay. Yeah. Good. Yeah. That's another way of saying it. But no. But so who has heard this expression? Something being vanilla. Okay. Almost everyone else. Okay. So no, it's fine. I mean, and so the problem with textbook is, right? So what is the textbook variant, right? Sort of. Let's maybe get to this. If we go to El-Gamal, right, our public key is just G to the X, secret key is X, and now a ciphertext, let's say, whoops, enc pk of a message M is, well, we have G to the R, that's always the same. Let's call this thing here H, whoops, H, right? And H to the R times what? Right now, what matters is the encoding of the message, right? But not for CCA security, right? You could encode the message here however you want. The scheme would not be CCA secure, right? But the encoding does matter when we want to take things the other way, right? When we looked at security, this homomorphic property was bad because it kind of interfered with the security notion we wanted to achieve, CCA security, right? But now let's turn things on their head and say, wait, okay, this ability to manipulate ciphertexts was bad in the in terms of reaching the maximalist security goal. But let's say we're fine within CPA security. We know that El-Gamal under the DDH assumption achieves in CPA security. Right? Let's say we're fine with CPA security. We don't want more than CPA security. We don't want the maximalist goal of CCA security. Now, what could we get out of this ability to manipulate messages? And the simplest thing one could do now is, for instance, say, e.g., encode is G to the M. Right? Then ciphertexts are G to the R, comma, G to the R times G to the M. Good. And now let's call it R1 and M1. And let's call this C1, and let's call C2 is C to the G to the R2. Oh, this should be an H. And here H to the R2 times G to the M2. Okay, now what can we do here? We can just multiply these two ciphertexts. Let's say we multiply them pointwise, right? Then we get some C3, which is G to the R1 plus R2, comma, H to the R1 plus R2 times G to the M1 plus M2. Okay, and if we decrypt this ciphertext, now of course the question is again how do we decode this encoding? But let's say M1, M2, and M1 plus M2 are such that we can compute discrete logarithms efficiently. Say M1 and M2 come from a small range. Let's say from let's say for now they're 0, 1, right? Then M1 plus M2 is 0, 1, or 2, right? So I can effectively or efficiently brute force what my M1 plus I can efficiently brute force the discrete logarithm of G to the M1 plus M2, right? And I have computed this ciphertext without knowing what M1 and M2 were, right? So you can just give me these ciphertexts, and now I can blindly compute a ciphertext which encrypts the sum of these two messages. That's the most basic homomorphism we can think of, additive homomorphism. And well, the El-Gamal scheme has this. So we knew how to construct encryption schemes that support additive homomorphism basically since the beginning of public key cryptography. Right? So additive homomorphism was always something natural, and as we've seen earlier, was seen as something bad, right? Because it allowed for certain kinds of attacks. It made the El-Gamal encryption scheme less secure than the Kramer-Shoup encryption scheme, right? But now we're looking at this from a functionality perspective. So additive homomorphism, the first time this people started to be interested in this was in the, let's say, 1990s, at some point in the 1990s. So what could you do with an encryption scheme that just allows you to sum things up, or to use a different word, to tally things up? What could you do with this? Right? Every one of you sends me an encryption, so to speak. Let's say I'm entrusted with computing the homomorphic sum of all your ciphertexts, and then someone else decrypts. What is this? So if every one of you sends me an encrypted message with, let's say, a bit, and I'm homomorphically computing a sum, and then some other trusted authority decrypts. What is this? Yes? No, yes?
Perhaps voting?
Exactly, it's an election, right? So this additive homomorphic property started to be interesting when people were interested in implementing elections with cryptography, right? This is still a hotly debated topic, right? Because you don't just want privacy in elections, right? It's not enough that in the end I don't learn who you voted for, right? You want a little bit more, right? What's the obvious problem if you all send me your votes and I homomorphically tally them up. Yes?
If you, for example, for which person I was voting for, you can add my number multiple times.
For instance, that, but even simpler, I could just not perform the tally as I was supposed to. I could maybe create a few new ciphertexts and add things in. I could buy a thing. So verifiability is another important property of elections, which might not, which doesn't come easily. Right, and it doesn't even stop there. Then there's another problem called coercibility. Is anyone familiar with this problem of coercibility in elections? So in Germany, this is traditionally not a great problem, but for instance, in Italy, it is forbidden by law to take your cell phone into a voting booth. Why is that? I could take a picture of what I voted for, right? So, I mean, traditionally organized crime, which tries to coerce people into voting for certain candidates, like, let's say, selling votes, is an enormous problem, right? You don't want elections where I can sell my votes to someone. And in Italy, what has happened, and they have strict laws against this, is that people would go to the voting booth and either take a picture of how they voted or film themselves how they're voting for a certain candidate, and then get a monetary reward in return. Right? So this is not the point of democratic elections. So it doesn't even stop at verifiability. You also want properties that prevent coercibility, incoercibility notions. So elections is really a very complicated topic. And of course, here, if I got to vote online with El Gamal, I would be immediately coercible. Right? Or I could immediately prove who I voted for, because what do? I send my ciphertext encrypting my vote for a certain candidate to the voting authority. Let's say this is public, right? They're going to write my encrypted vote on a bulletin board. Let's say you want verifiability. But then later, I could go to someone and open to this person the random coins are, proving that I voted for this person, and this should not be possible. So if I just use El Gamal to let's say encrypt my vote in an online election, I could later prove who I voted for, which should not be possible, right? So there's many pitfalls when it comes to electronic elections, and yeah, those are just a few. It doesn't even stop there, right? It's a way more difficult problem. But this is sort of after 30 something years of probably already, yeah, 30 years of research in this area. In the beginning, they were like, great, homomorphic encryption. Now we can do online elections. But good. This is just for sums. But great, sums are good for being able to compute sums, is good for elections or tallies. But what about more expressive computations? Is an addition good enough to perform arbitrary computations? Or asking differently, is addition over any, let's say over the integers, over some finite field, is that a universal gate? Can we implement any computation with additions? Yes, no, maybe.
Theoretically, I think yes, you could do multiplication or exponentiation by just adding elements, but it will be unfeasible.
What do you mean? I mean, So if the only operator, let's say you have is that you have is an addition gate, right? Of course, in terms of defining operators, let's say multiplication, you define it via addition. Addition is enough to give rise to all the other operators. But yes?
I think the problem is that if we just add two numbers, we don't, I mean, in this case, we don't have to know what the values are, but if we want to implement multiplication through addition, we have to know at least what one of these numbers was.
Exactly. So you couldn't do a multiplication of two hidden values, right? If you just iterate addition of something by itself many times, then you know you have a secret value, but there's a secret value, but then there's a multiplier, and you know what that multiplier is, right? So you cannot, if you have homomorphic addition, it doesn't give rise to homomorphic multiplication. So addition alone, in fact, is not, or XOR, right? Let's go modulo 2. XOR is not a universal gate. So what are some universal gates, or the most famous universal gate that gives rise to all other binary logic gates? Yes?
NAND gate.
The NAND gate, exactly. So, the NAND gate is a so-called universal gate, right? And with addition alone, we cannot do NAND gates. But if we have addition and multiplication, right, then all of a sudden we can do NAND gates. In fact, with once you have addition and multiplication, you can do any, you can implement any lookup table. You can kind of implement any gate immediately. Maybe you know, next time or so, let's do at some point another exercise. You know what we could do? We could do an entire lecture with exercises like this, just as a add plus mult any gate exercise any gate, e.g. NAND. Good. Okay. Now that we're there, addition is not enough. We need addition and multiplication to get interesting things. But now let's give ourselves an encryption scheme. And the cool thing is, when we look into homomorphic encryption, the textbook or vanilla security notion will always just be in CPA security, right? I'm encrypting something, and without giving the adversary additional capabilities, I want that this value is hidden. And that means that in terms of security, we can just stick within CPA security. But the property that we're now sort of tweaking is not security, but just correctness, right? For homomorphic encryption scheme, we don't just want that you, when you encrypt the message and then later decrypt this ciphertext, that you get the same message. You also want correctness with respect to homomorphic operations, right? And this is now a feature that we typically call homomorphic correctness. Good. So now let's look into this. So let's take ourselves an encryption scheme, a public key encryption scheme, keygen encdec, could also be private key. We say it's homomorphic for a class F of functions, where m from m to the n to m, right? N could be whatever, some small constant or whatever. Sorry, the little n is a small constant, and m is the plaintext space. We say it's homomorphic if we have an additional algorithm, which we call eval. Right? Typically, in a homomorphic encryption scheme, we already put this eval algorithm into the signature of such an encryption scheme. We typically write keygen enc dec eval. Right? We have this additional algorithm, and it takes as input potentially the public key. Up here, we've seen it doesn't need the public key; it just takes ciphertexts. So public key, a function f, and ciphertext C1 to Cn, and outputs a ciphertext C hat. We say that a homomorphic encryption scheme keygen enc dec eval is correct if it holds for all lambda, all tuples of messages, and all functions f in this class f, that if we decrypt the homomorphic evaluation of f on C1 to Cn, where the Ci are encryptions of mi, then this is just f of m1 to mn, right? So the process is I encrypt the messages, I homomorphically and blindly, that's the important thing, I evaluate homomorphically without knowing the secret key, get an output ciphertext, and then decrypt. And then I want that the result that I get from decryption is the same that I would have gotten if I didn't do any of this encryption stuff and just took the messages M1 to Mn and applied the function f to it. Okay? So this is homomorphic correctness. Are there any questions about this? Yes?
So the function f takes multiple arguments as parameter.
In the simplest case, it just takes two things, right? Let's say we want to compute a sum of M1 and M2, then it just takes M1 takes two arguments. Right here, this is just for sake of generality to say that, well, we have an n-ary function f, but think of binary functions that just take two arguments.
So the idea, if I understand correctly, is whether the evaluation of several ciphertexts, that this should be the same thing as the combination of the corresponding plaintext.
Exactly.
Itself, but you can plaintext.
Exactly. So again, basically, homomorphic correctness means that if you perform a computation on ciphertexts and then decrypt, right, then this should be the same as all this without encryptions and ciphertext and whatnot, and just a plain text evaluation of f on these messages. Good. Okay. In order to actually look at our non-trivial homomorphic encryption scheme, the thing will have a caveat, but we will still need something or a slightly more powerful type of algebraic structure. Namely, we will look at groups of composite order, right? I mean, since you all went through the undergrad cryptography lecture, I'm not telling you anything new by saying that if I give you a composite number n, which is a product of two large primes, then it is generally assumed that recovering these prime factors is hard. This is the factoring problem, right? And so far, we've only looked at groups of prime order, right? A group which has p elements. But now, for the sake of this upcoming construction, we will look at groups with composite order, where let's say the order n is public, but the factors p and q are unknown, right? This is sort of not a publicly generatable group, but it needs to be a privately generated group, right? So far, for essentially all schemes that we've seen, we assumed that the group G is part of some publicly known parameters, actually a fixed group, right? There's this famous group, this adds 25519 group, right? This group of order 2 to the 255 minus 19, right? And that's a publicly known group with a fixed group with a fixed order. But here we're gonna use groups that cannot be publicly generated, because if they were publicly generatable, then you would somehow probably know the factors p and q, right? So there needs to be some form of private generation. Good. And that's why we're now explicitly talking about a group generator. You can do the same thing for prime order groups, but here, there is kind of optional, but here it's really necessary, right? So in the following, we'll assume that there's an efficient algorithm group gen, which just takes the security parameter and outputs a description of a composite order group with a generator G and a factorization of the modulus n, which is p times q, right? So there does come some, when you run this group generator, you do get some, let's say, trapdoor out of this, which is the factorization of this modulus n. And furthermore, we will assume that there is such a group, or a family of groups which can be generated by such a group generator, which is also equipped with a bilinear map. All right. Good. And a quick reminder, if this is a, did we say, good. A quick reminder is that any such group G is isomorphic to Zn, right? Why? Okay, I'm already writing this here, so there's no point in asking this as a question. So we know that any prime order group is isomorphic to ZP, right? So how does this work? How can you see that any prime order group is isomorphic to ZP? Well, basically, what we do is give me any G in a prime order, any element G, right, in a prime order group G, and look at this homomorphism phi, which goes from the integers into G by sending, let's say, an x to G to the x. Right? This is a group homomorphism, right? We can easily test that, and now we just need a tiny bit of group theory, right? Now we know that the kernel of phi is a subgroup of Z, right? Kernel kernel of phi is a subgroup of Z, right? But another thing that we know is that P is in the kernel of phi, right? Because again, the group order is P, so G to the P is equal 1. Whoops, what's happening? P is in there, and now now we're basically basically done, right? If so it means P times Z is in the kernel of phi. So now we could ask, is kernel of phi a proper subgroup of P times Z? But then by Lagrange theorem, this would mean that the order of kernel of phi is a divisor of P, and we know only 1 and P are divisors of P, right? So this means we do get an isomorphism between ZP and G, right? This is really just a small bit of group theory. You need Lagrange theorem for that, but I'm not gonna open up this entire can right now. So any prime order group is immediately, by Lagrange theorem, isomorphic to ZP. And now Zn has two non-trivial subgroups, Q times Zn, which is isomorphic to Zp, and P times Cn, which is isomorphic to Zq. And I'm even talking about Lagrange theorem down here. So now GP, we can let GP be the subgroup of G isomorphic to ZP, and GQ be the subgroup isomorphic to ZQ. So if G is a generator of G, then G to the P is a generator of GQ, and G to the Q is a generator of G to the P. And hence, by Lagrange theorem, it holds for every H in GQ that H to the Q equals 1. Good. So we've constructed these two subgroups, and all there is left is, well, by Chinese remaindering, Zn is isomorphic to Zp times Zq, right? And now we just have to plug all these homomorphisms together, right? We've seen that Zp is isomorphic to Gp, and Zq is isomorphic to Zq. And we finally get that Zn is isomorphic to G. Oof. Okay, good. But that was a small algebra detour. Good. Now let's get into more some, again, more cryptographic things. So in composite order groups, we can make a natural generalization of the DDH problem, right? And recall from further that the DDH assumption asks that, or one way of seeing the DDH assumption is, I'm giving you a matrix where each group, where each entry of the matrix is encoded as a group element, right? I'm giving you G to the X, let's say a matrix M I'm just writing a DDH quadruple as a matrix, G to the Y, G to the XY, right? Now I'm asking you whether a given matrix has rank 1 or rank 2, right? Obviously, if it's a DDH tuple, it has rank 1, right? Because the second column here is just the first column raised to the power of y. This was this linear algebraic perspective on the DDH problem. So good. Basically, I'm giving you a matrix M. In one case, it has rank 1. In the other case, it has rank 2 or full rank, right? If I replace G to the XY with G to the U, I'm just getting a random matrix, except for the, I mean, if I choose the generator randomly, I'm really getting a uniformly random matrix. Good. In a way, this is equivalent to asking whether the matrix M generates the entire group GP square or just a one-dimensional subgroup of the a one-dimensional subspace of ZP square. Okay, so does this is if it's a full rank matrix, it sort of spans the whole space. But if the matrix M is rank deficient, it only spans a one-dimensional subspace, right? Again, in the first case, in the first case, the two columns of the matrix are linearly independent. The second case, they are linearly dependent. Good. And now here's a generalization of this concept to the setting of composite order groups, right? Let's say we're generating ourselves a composite order group G, and together with a generator G in order N, and now we're choosing ourselves a uniformly random R. And the subgroup indistinguishability problem now asks us to distinguish the following two distributions. On the one hand side, I'm going to give you the group G, right? Because the group is now privately constructed. I need to give you the group. It's not some common knowledge what this group is. I'm going to give you the group and just G to the R, right? And recall that G generates the entire group. On the other hand, I'm giving you G to the R times P. This does not, G to the R times P, right, is, again, G to the P to the R. And recall, we said G to the P generates a subgroup GQ. Generates a subgroup of order Q. So it does not generate the entire group. Okay? So in algebraic terms, the group on the right-hand side, or the, let's say the generator on the right-hand side, this G to the R times P generates a strictly smaller group than G, whereas this G to the R generates the entire group G, right? So G to the R is a uniformly random element in G, whereas G to the R times P is a uniformly random element in GQ. So this assumption asks us whether an element H that we're given generates all of G or only the subgroup GQ, right? And so far, I think we're at the end, and I think we can leave it here. Now the subgroup indistinguishability assumption now just postulates that these two distribution, one uniformly random in G and two uniformly random in GQ, they're indistinguishable. right? So it's you cannot, there is no efficient mechanism to tell whether something was uniformly chosen from the entire group or an unknown subgroup. Good. We're going to leave it at this. And yeah, so probably I'm going to finish this up next time, and then we're going to do an exercise session, because now I think we've collected a lot of different exercises that we can go through together. That's all. Thank you.